Increasing the vehicle's torque and improving fuel efficiency sounds hard without any special upgrades or tricks. However, using a variable intake manifold makes it very easy. A variable intake manifold is able to change its runner length, improving volumetric efficiency at both high and low engine RPMs. This is achieved by using a set of valves within the inlet manifold. These valves can be operated by a vacuum solenoid or an electrical actuator. The ECM will command the valve's operation to optimise the engine's power and torque across all driving conditions. Depending on the engine's configuration, there may be more than one vacuum or electric actuator. On a V-configured engine, there may even be one for each bank. This means the ECM can set high, low, and signal performance codes for each bank. Looking at this vehicle schematic, we can see the intake runner solenoid receives its control voltage from the powertrain relay. The ECM grounds this circuit to control the operation of the intake runner valves. In this module, we'll be looking at faults within the vacuum actuator, linkage assembly, and the solenoid. A quick test is to activate it with a scan tool while listening to the solenoid. A better way to test this circuit is to disconnect the harness connector at the solenoid and use a multimeter. Place the red lead on the voltage supply terminal and the black lead on the control terminal. Using a scan tool, command the valve to activate and watch the meter display. We should see battery voltage in a correctly operating circuit. Some ECMs use a PWM control to operate the solenoid valve. The only way to test these circuits correctly is with an oscilloscope. So now that we know what a good circuit looks like, let's test some different fault scenarios. To test the voltage supply terminal for either an open or excess resistance, turn the ignition off. Attach the black meter lead to battery negative and the red lead connected to the voltage supply terminal. Turn the ignition on. Again, you should see battery voltage. If less than this or no voltage is seen, there may be excess resistance or an open in the circuit. Confirm the terminal tension is correct and free from corrosion, as this may also induce the fault. If the harness connector at the solenoid is okay, remove the supply fuse and perform a visual inspection to confirm the fuse continuity. Remember to confirm your visual inspection with a continuity test of the fuse itself. If this is okay, check for battery voltage at the supply side. If 0 or less than battery voltage is seen, there is an open or excess resistance in the powertrain relay circuit. Further investigation here will be required. With the fuse removed, test for correct terminal tension and check for any corrosion. If voltage supply to the fuse was okay and there was no evidence of corrosion or spread terminals, the fault would be between the fuse block and the solenoid harness connector. If the fuse was open, there's a good chance there's a short to ground within the voltage supply circuit. With the ignition off, the fuse removed and the harness disconnected at the solenoid, attach the red meter lead to battery positive and the other connected to the supply terminal in the connector. Turn the ignition back on. If any voltage is now displayed, we have confirmed a short to ground in the harness between the fuse box and the solenoid connector or adjoining circuit. It may be necessary to locate and disconnect any component in that circuit to isolate the cause. If no voltage was displayed during the test, the fault must be in the vacuum solenoid. To test the control circuit for an open or excess resistance, turn the ignition off and disconnect the solenoid connector. Place the black meter lead on the control terminal and the red connected to battery positive. Turn the ignition on. With the scan tool, command the solenoid on. If battery voltage is seen on the meter display, the ECM control and circuit is okay. But if battery voltage was low or not seen, move the black meter lead and back probe the control terminal at the ECM while performing the same scan tool command. If the correct voltage is now seen, there is an open or excess resistance in the control circuit between the two connectors. If battery voltage wasn't seen during this test, turn the ignition off and inspect the ECM connector for terminal tension and corrosion. If this is found to be okay, the fault must be within the ECM ground control. To test for a short to ground in the control circuit, place the red meter lead on battery positive and the black lead at the solenoid control terminal of the harness connector. Turn the ignition on. If any voltage is displayed, this confirms a short to ground in the circuit. Turn the ignition off and disconnect the ECM harness connector and turn the ignition back on. If the voltage disappears, then the short to ground is within the ECM or a circuit from the ECM. Perform a continuity test between the control terminal in the solenoid connector and all other terminals in the ECM connector. If continuity is seen, there is a short in the circuit. However, if there was no continuity displayed, the short to ground is in the ECM itself. To test the control circuit for a short to voltage, turn the ignition off and disconnect the solenoid harness connector. Place the red lead on the control terminal and the black meter lead on battery negative. Turn the ignition on. If any voltage is displayed, a short to voltage has been confirmed. Turn the ignition off, disconnect the ECM and turn the ignition back on while watching the meter display. If the reading has dropped to 0, the short to voltage is within the ECM or a circuit from the ECM. To isolate between the two, perform a continuity test between the control terminal in the solenoid harness connector and all other terminals in the ECM connector. If continuity was seen, the short to voltage is within that circuit and the control circuit. If no continuity was seen, the short to voltage is in the ECM. But if the voltage remained with the ECM disconnected, the short is within the wiring harness between the two connectors. If we have proved the electrical side to be correct, we still need to test the vacuum actuator and solenoid to ensure this system is working. Connect a vacuum gauge to the solenoid supply hose and start the engine. Always refer to the manufacturer's specifications for inlet manifold values. If no or incorrect vacuum is observed, check all hoses for any kinks, twists or splits that may affect gauge readings. If this is okay, check the intake manifold for any blockages or leaks that may also affect the vacuum supply. Now let's move the gauge to the working side of the solenoid. With a scan tool, command the solenoid on with the engine running. We should see the vacuum gauge needle correspond to the scan tool commands. If no gauge reading is observed, there is a fault within the solenoid valve. If there were no concerns on either side of the solenoid valve, move the gauge to the vacuum actuator and repeat the test. If no vacuum was seen, check the hose for any kinks, splits or twists that may impede the gauge operation. If the correct value was seen on the gauge, we need to test the actuator with a hand-operated vacuum pump. Apply a vacuum to the actuator while watching the gauge. If the needle doesn't show vacuum or the pressure slowly rises, there may be a fault within the diaphragm. If vacuum is held, watch the linkage for movement. No movement could indicate a seized linkage or intake runner. Depending on the type of vehicle, the intake manifold may need to be removed from the engine to test the linkage and valves. Any major faults should be immediately visible, whether they be linkage or valve related. Understanding how a variable intake runner system works makes diagnosis and repair of these components a little less stressful while giving your shop an edge over the competition. Thanks for watching. Bye for now.